All right, I think we're recording. Good morning again, everybody. So last time we start talking about the mathematics behind inverse problems, and then what we learned is that thorough understanding of the underlying principle or the governing principle in a particular phenomenon is very pivotal. Actually, hindi nga lang pivotal, pero imperative siya in studying any inverse problem regarding that phenomenon. Hindi natin kayang i-predict kung ano yung kailangang input para makuha yung isang appropriate or desired output if we don't have an understanding of how the process is being carried out or how the phenomenon behaves, right? So kaya kailangan talaga maintindihan muna natin yung phenomenon itself, right? And when we say understanding the phenomenon, we want to build a mathematical model for it. Usually it's an equation that relates the inputs to the outputs. And then to make or to have an easier time analyzing inverse problems in general, parang pinag-aaralan natin to in terms of operators. So instead of just an equation, so we will phrase it so that we have an operator. So that operator lang ginagamit kong term kasi we are not just restricted to the usual functions that you learned in algebra, wherein you have a set of real numbers being mapped by the function to another set of real numbers. Ngayon, mas generic na. Yung ating domain para dun sa mga functions na i-consider natin that will define our phenomena ay pwedeng mag-admit ng kung ano-anong mga bagay. Pwedeng mga matrices yung pinag-aactan ng ating function. Pwedeng function siya na ang domain ay a set ng functions, right? And these are what we call operators. And that's basically what we did last time. We familiarize ourselves with the use of operators, the different and various notations for operators. Nakilala natin yung mga usual operators na nakasalamuhan nyo na in elementary calculus, which are the derivative and the definite integral operators. We also look at the gradient, the divergence. I don't nagka-time to tackle the curl, right? Pero ang idea rito ay napaka-generic ng functions na kino-consider natin, and hence we call it by a fancier name, operators yung tawag natin. And a peculiarity of operators, we can map an infinite dimensional space into a finite dimensional space. And I think that's one of the examples we have seen last time. We're in, halimbawa, nasa na yun? Right, the definite integral operator. So we are mapping the set of all continuous functions on a closed interval AB. Ano yung dimension ng set na yan? Infinite yung dimension niya. Right? So hindi siya two-dimensional, hindi siya three-dimensional. Infinitely or infinite yung dimension ng set of continuous functions. Meanwhile, yung set of real numbers, one lang yung dimension niya. So you see the power of operators. We are mapping an infinitely dimensional domain, all right, or input space towards a finite dimensional, pinakamababang dimension pa nga yung kinuha nating codomain. All right? So perhaps you can study the effect of the dimensionality of the input space and the output space later. Pero yun nga, gusto ko lang i-drive na point dito yung generality ng operators vis-a-vis kung ano yung mga usual functions na na-consider natin last time. Right? And with a rough understanding or a rudimentary knowledge of operators, probably we can start talking about the different characteristics of inverse problems, right? Or in general, we'll tackle the different characteristics of a problem, a mathematical problem in general, and we will see that unfortunately, most inverse problems do not possess yung mga ideal properties na gusto natin from a mathematical problem, right? And that's what we'll do. Second chapter ng module 2, ill-posedness. Okay. Now, ill-posedness is one bad property of a math problem. Meaning, if a problem is ill-posed, we need to be extra careful in dealing with the solution. This means that the usual textbook solutions that we learned, like for instance, inversion, right? Kung meron kang operator, so halimbawa, meron kang operator M that maps your input space, whatever that input space is, towards your output space. such that halimbawa, yung input x, tineturn niya into mx, right? Or the image of x under the operator curly m, right? So, ang idea, kung tawagin natin itong y, right? So, the inverse problem is solving for, say, an x such that it will give us a desired output. So, we want to solve this equation, right? So, mx equals f. So, si f halimbawa, kunin ko na itong y. Si f halimbawa yung gusto nating output, right? This is the inverse problem. We want to find what is the necessary input x so that we get the desired output f, right? So yung textbook solution na natutunan natin ay, okay, meron akong function, so I will be hoping that I can invert that function. I can find the inverse of that function or that operator, because if I'll be able to do so, kaya ko lang i-apply yung inverse ng isang operator to one side para makuha kung ano man dapat si x. So for instance, if we know that m, the operator curly m, or if you want the function m is invertible, so ang gagawin ko lamang, i-apply ko lang yung m inverse to both sides, right? Tapos sa property ng composition ng functions, sila ay siya ay associative. So yung left-hand side, pwede kong isulat na m inverse m x equals m inverse f, right? So iniba ko lang yung grouping. Imbes na i-group ko si m at saka si x, ginroup ko muna si m inverse at saka si m, right? Now, m inverse and m, so dahil sila inverses ng isa't isa, they will just reduce to the identity. Identity operator applied to the input x will just give us x, so that means x is equal to m inverse f. And that should have been the end of story, right? Masaya na tayo dapat dito, right? Pero yung challenge dito, una, paghahanap ng m inverse. How do you compute the inverse of the operator? But if you're lucky enough to know what the inverse of your operator m, then you might be saying na, okay, tapos na yung boxing, eto na yung final solution ko. Ang desired input ko ay m inverse of f. Well, unfortunately, this will only work for well-posed problems. There's no wrong mathematically with this solution scheme. All right? As long as m is invertible, then this should have been fine. However, kapag ka ill-posed yung problem, this solution might not be enough. At yun yung titingnan natin. Kailan ng isang problem ay ill-posed? At bakit karamihan ng mga inverse problems ay ill-posed? Or basically, ano yung implication ng pagiging ill-posed ng isang inverse problem to the solution at saka sa practical applications? Right? Now, ano ang ill-post or kailan nagiging ill-post ang isang problem, kailangan nating i-tackle yung negative. Ano muna yung magandang klase ng problem? And we call a nicely behaved problem in the sense of finding solutions to be a well-posed problem o yung well-postedness property. We will adopt what Jacques Hadamard characterized as a well-posed problem. Sabi ni Hadamard, ang isang well-posed problem, meron siyang tatlong properties. Una, the problem should have at least one solution. So, existence muna ng solution. Siyempre, hindi magandang mag-solve ng problem na wala naman nag-exist na solution. Tama? So, we need to guarantee, okay, dapat merong isang solution. Second, the problem has at most one solution o yung uniqueness ng solution. So, kasi kapag ang isang problem ay maraming posibleng solutions, how do you distinguish one solution from the other? How do you select one solution over the other available solutions? So yun yung isa pang problema. So kasi gusto natin sa well-postedness, madali siyang hanapan ng solution. At kapag marami kang options or maraming possible solutions, then how do you pick which of them to choose, right? So kaya kailangan gusto natin H2, the problem has at most one solution. So H1 plus H2, right? Property H1 and property H2 should imply that a well-posed problem should have exactly one solution. So existence and uniqueness ng solution. So if I'll ask you to show that the problem is well-posed, so kailangan ipakita nyo or gumawa kayo ng isang existence and uniqueness proof. All right? So ibig sabihin, So far, so good. Itong problem natin ng inversion. Kasi nangyayari to kapag si M ay invertible. Halimbawa sa linear algebra nyo, kung meron kayong matrix na invertible, yung solution ng linear system characterized by that matrix. So kung meron kang matrix M times a known vector X equals a right-hand side. If M is invertible, then sabi ng there will exist a unique solution for your linear system. And then kung H1 at H2 lamang yung kailangan para maging well-posed, then probably any system of linear equations with invertible matrix coefficient or coefficient matrix should be well-posed. Pero hindi natapos doon yung requirement ni Hadamard. Kasi alam niya na may posibilidad na hindi pa well-posed or hindi pa nicely behaved yung function kahit invertible yung operator na nagde-define dun sa problem. That's why he adds a third condition. He said that for a problem to be well posed, hindi sufficient na merong exactly one solution, pero kailangan ko si property H3. What is property H3? The solution should depend continuously on the given data. In simple terms, ibig sabihin, kapag merong kaunting change doon sa data, doon sa problem, dapat maliit lang din yung change na nakokos niya doon sa solution. Alright? So yun yung ibig sabihin ng the solution depends continuously on the given data. This terminology, yung H3 yung pagkaka-state dito sa handout, ay medyo mathematical. You'll be talking about continuous dependence. Parang kailangan yung i-review yung konsepto ng continuity. When do we say that a function is continuous on its domain? Ganun din dito. Pero in a nutshell, pag pina-explain ko sa inyo yung H3 to a layman, ibig sabihin niya lang, kapag meron kang maliit na change dun sa data, dapat maliit lang din yung change dun sa solution na ma-obtain mo from the perturbed data. Okay? So, but mathematically, that is the concept of continuity, as you will see in our first example of a well-posed problem, right? Now, my first example of a well-posed problem is yung problem natin of finding or the inverse problem of finding what should be added to 2 to get the number 5. So remember last time we phrase it this way. Our forward operator is a function f that will take a real number to another real number. Tapos dahil yung problema natin ay addition by 2, right? That's the phenomenon that we are considering. Again, the inverse problem is what should be added to 2 to get the number 5. Yun yung inverse problem. The forward operator is this. Addition yung addition yung underlying principle. So kapag meron kang real number x, imamap natin siya sa 2 plus x. Ito yung forward operator. Because if you know the input x, yung output ay mako-compute by adding 2 to x, right? So this is our forward operator for that inverse problem. Now, in a nutshell, or in a more conventional way, pwede nyo isulat si f as 2 plus x, right? And then what do we know about 2 plus x? 2 plus x is a linear function, so this is bijective. Ito yung in-note natin last time. Dahil to ay bijective, ibig sabihin siya ay invertible, right? Dahil siya ay invertible, so there exists an f inverse. Ano yung f inverse? Actually, si f inverse ay hindi na to there exists kasi si x inverse. Anyone remember what f inverse is? Kung ang x ko ay 2 plus x, ano yung x inverse? Ko-compute pa? Guys, ano si f inverse? Kung si f ay 2 plus x, ano si f inverse? Or nakalimutan niyo na pag-invert? Oh, thank you, Trisha and Daryl. Bakit may question mark, Daryl? It's x minus 2, right? So, ibig sabihin, kailangan mo lang i-ensure na kapag thank you, Alex, then, right, x minus 2 is correct. Because if you compose f and f inverse, either starting with f or starting with f inverse, you get the identity map x, right? So, si x minus 2 ay yung inverse. So, if I want, and f inverse is also bijective, properties ng functions, right? So if we want to answer the inverse problem, what should be added to 2 to get 5? That means the solution will just be f inverse of 5, right? Which is basically equal to 3. So there is a unique solution, right? So there's a unique solution to our inverse problem. Now, okay, so H1 and H2 are now satisfied. May nag-exist na solution, which is 3. So you can do it by proof by example. Remember, yung existence theorem, sa kanila lang nagwo-work yung proof by example. Because if you'll be claiming that there exists a solution, it suffices to give an example of a solution, right? So, okay na, meron na tayong solution 3. And then, uniqueness. Pwede ninyong i-argue na unique yung solution kasi bijective yung inverse. Or you can do it old school. Pwedeng gawin nyo ay suppose there are 2 solutions and then you'll show that they are equal to each other. All right? So classical proof ng uniqueness. So H1 and H2 are satisfied. Well, how about H3? So how do we satisfy H3? Well, si F inverse ay linear, right? And we know that linear functions are continuous. Meaning, kapag ka nagbago ng konti yung data, so in this particular case, our data is the right-hand side, right? Dun sa inverse problem of looking for what is to be added to 2 to get 5, ang ating data ay si 5. Kasi si 5 yung gusto nating ma-generate to be the to be the output. So in an inverse problem, the data is the desired output. So our output, the desired output is 5, so that's going to be our data. So meaning kapag ka binago ko ng konti si 5, konti lang din ba yung mababago dun sa makukuha kong result. So if, for instance, instead of 5, ang ginawa kong data ay, or ang ginawa kong desired output is 5.01. So kung si 5 yung output, this is the original data in the problem. So si 3 yung solution sa ating inverse problem. If I vary the data a little bit, say I'll turn it to 5.01, what would be my solution? So my solution would be what? The solution would be 3.01. So yung 0.01 na pagbabago doon sa data caused a 0.01 change in the output. Maliit lang din yung change sa output. Or dun sa medyo balibaligtad pala yung output dun sa nakuha natin na solution, right? So a small change in the data, which is the desired output, yielded a very small change, or actually a correspondingly small change in the solution, which is the necessary input, right? Pag ginawa ko tong 5.0001, makukuha ko na output ay 3.0001. So maliit na change sa data, maliit na change sa input, or dun sa computed input, then this is well posed. Pero the actual, so ito ay example lamang, specific perturbation, so specific small changes in the desired output yielded, you can say small changes in the input as well, right? Or in the computed input as well. So this will give us an idea that probably this problem is well posed. Pero paano natin ma-argue yung talagang pagiging well-posed niya? Kailangan ipakita natin that the problem or the solution depends continuously on the given data. And how can we do that here? Well, we will borrow the concept of continuity. All right. So how do I say this? Well, I can argue it F inverse is continuous. Kasi yung solution scheme natin ay si F inverse, right? So I can say that F inverse is continuous on the set of real numbers. Ano ba yung implication ng continuity? If you remember the definition of continuity, maganda sana ipapa-recite ko pero ang sabi niya, for all epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus a is less than delta, then f of x minus a f of x minus the limit, f of x minus L, which actually is continuity nga pala, minus f of a is less than epsilon, right? So sa kahit anong epsilon greater than 0, there exists a delta such that if x and a are delta units away from each other, okay, the function values will be within epsilon units from each other. Pero natutunan natin kapag ka linear yung function, ang slope ay 1, yung delta equal lang kay epsilon. Kasi nga si F inverse natin dito, actually F inverse. So dapat si F inverse of x ay equal kay x minus 2, right? Ang slope nito ay 1. Tapos ginawa niyo sa Math 36 pag-prove ng continuity para sa isang function na ang slope ay m, right? Ang pinipiling delta ay epsilon over m. That's why I know here na kapag ka si x pero ang value ni x mula kay a ay kay epsilon, meaning there is an epsilon change in the input. The input from x naging a, pero ang difference nila ay epsilon lamang. And remember, epsilon stands for a very small number. So you can say this is a very small change in the input. Nagbago yung input or yung data mula kay x papunta kay a by a small amount, say an amount epsilon. The continuity of F inverse implies that the change in the function values, namely F inverse of x and F inverse of a, will also be within epsilon units. So ibig sabihin, pag binago natin ng epsilon, yung data dun sa problem, or in the context of our inverse problem, pag binago natin yung desired output by an amount epsilon, yung mababago dun sa solution na ma-obtain natin for the inverse problem ay also epsilon units. So that means there's a small change in the input will cause a small change in the input. A small change in the data will yield a small change in the computed solution. That means this inverse problem is well posed. Okay, so meaning traditional reconstructions or traditional solutions like the inversion of the operator will be sufficient for this particular problem. All right, is that clear? At least yung idea, is that clear? Or ang dami palang kailangang aralin dito sa course na to, no? Yun yung isang disadvantage ng special topics course. I can get some concepts from different courses that you have taken before, you know. Pero I hope the idea is clear, right? Ang mahirap lang naman yung H3. Pero ang essence lang naman ng H3, pag binago mo ng konti yung data, konti lang din yung nababago sa input. How do we analyze it? Medyo mahirap kapag ipapakita na siya ay nasa-satisfy. Mas madaling i-prove na hindi siya nasa-satisfy, right? But if you will extrapolate from this discussion that we have, right? Kailangan nyo lang ipakita na yung inverse operator, all right? Or yung solution operator ay continuous. All right? Or there's some sort of continuity aligned with the inverse operator. Okay? Pero mahirap tong gawin kasi pag de-design nga ng forward operator, medyo mahirap na minsan, much more yung pag-i-invert niya. Okay? So kaya usually, magre-rely tayo dun sa assumption ng inverse problem na sinosolve natin ay ill-posed. Alright? Hindi na tayo mag-hope na siya ay well-posed because instead of using traditional methods, ang gagawin nating hindi lang tayo instead of using traditional methods, we'll be using fancier schemes which will involve regularization. So hindi lang inversion yung gagawin natin, kundi gagamit din tayo ng regularization techniques. All right? Now another example. One example of ill-posed problem is, say, finding an antiderivative of a function. Do you have any guess why this is ill-posed? Ayan, may nag-i-invite ng party sa Dota. So kailangan ko palang i-close yung Steam ko. Anyway, so why do you think finding the antiderivative of a function is not well-posed? Yun pala, pagka ang isang problem ay hindi well-posed, ang tawag sa kanya ay ill-posed. Tricia is right. She said sa chat, may plus C kasi dun sa, I guess this is dun sa solution ng antiderivative, right? And that is correct. Pero can anybody else expound on that? Bakit tama yung sagot ni Tricia na ill-post yung finding an antiderivative kasi may plus C? Bakit? Ano bang ginagawa ng plus C? What is violated from H1 to H3? Okay, Victor says because C can be any number, right? At the implication on thank you, Raf, hindi po unique yung solution. And Daryl's also right. Hindi lang isa yung solution. So pag nagkukuha kasi tayo ng antiderivative of function, say we are considering the inverse problem of finding the function to be differentiated to get x squared, there are two options for the solution, right? So one solution is to find the indefinite integral of x squared dx. Kung Math 36 yung pinanggagalingan nyo. Pero kung tapos na kayo mag-Math 151, tapos shout out sa mga nag-151 dyan this semester, right? Ganito yung gagawin natin. If phrase natin siya as an ordinary differential equation, we'll be solving for the function f, right? Whose derivative is equal to x squared. Or perhaps I should use g here, right? Or actually, dito na lang pala. Dapat ito yung tinawag kong g, right? So we'll be solving for this ODE. We'll be looking for the function f such that x squared is its derivative, right? So pwedeng tingnan natin dito to be our operator as the derivative operator. So meron kang df, where d is the derivative operator, equals x squared. Hanapin natin ano yung function ng f na may derivative ni x squared. Pero sabi nga ni Tricia, pag sinolve mo yan, at saka ni, may isa pa nagsabi, yeah, but anyway, pag sinolve natin yan, makukuha natin ay x squared plus c. And c can be any constant, right? C is any real number because the derivative of any real number is equal to 0. So that means we have an infinitude of solution. Infinitely many yung solutions para dito sa inverse problem, automatically siya ay ill-post na. Right? So hindi na tayo pupunta dun sa mahirap na H3 na tingnan pa kung ito ay kung yung solution ay nagde-depend continuously on the data. All right? So kasi hindi nga unique yung solution. Now, there are lots of inverse problems that suffers from H1 from the non-satisfaction of H2, right? So to remedy this, lalo na kung nasa-satisfy naman niya si H3, si H2 lang yung hindi niya nasa-satisfy, pwede tayong mag-add ng additional constraints to our inverse problem. For instance, to remedy yung pagiging ill-post ng problem na to, we can look for a particular solution, rephrase the problem a little bit, add more restrictions to it. So in particular, we can, instead of solving the one-liner ODE, pwedeng system yung isolve natin. We might look for the function f, whose derivative with respect to x is equal to x squared on a compact set 0 to 5. Pag sinabi natin compact, dun sa mga hindi pa nag-155, ito ay isang closed and bounded set. So sa real numbers, madali lang naman. Ang pinakamadaling example ng mga compact sets ay yung mga closed intervals. Right? So we're looking for the derivative we're looking for functions whose derivative is x squared on the compact set 0, 5. And then we will add an initial condition that f of 0 is equal to 1. Well, you can call it an initial condition, or you can call it a boundary condition, depending on how you interpret x equals 0. Okay, hold on, guys. Or you can just call it a constraint, an added constraint to the problem, meaning we are constraining our solutions to satisfy a preset condition that will give us a unique solution. Okay, so kung ill-post yung problem, dahil lamang sa H2, pwede kang mag-add ng conditions. Ikaw na yung mamili ng conditions, what would be the ideal solution for you just to make the problem well-posed. All right. So in this particular case, if I will solve this equation here, I will get 1/3 x cubed plus 1. Teka, parang mali yung solution ko kanina. Sorry, ngayon ko lang na-realize. Ano sinabi kong solution kanina? Yeah. Sorry, hindi plus C. Alright? Kinopya ko lang yung x squared, dinagdagan ko lang talaga ng plus C. Sorry about that. Medyo maaga pa kasi. Alright? So that is 1/3 x cubed plus C. There would be infinitely many solutions. Pero nung nag-impose tayo ng initial condition, we said that we want f of 0 to be equal to 1. So dun sa infinite family of solutions, 1/3 x cubed plus C, pipili lang tayo sino-sino yung nakakasatisfy ng f of 0 equals 1. And for us to know which one of them, magpa-plug in lamang ako ng 0 para sa lahat ng x's. So lahat ng x's dito, papalitan ko lang ng 0. So ito ay magiging C equals 1. So we get the particular solution, or in this case, the unique solution to our inverse problem, or to our constraint inverse problem, siya ay 1/3 x cubed plus 1. So nasatisfy na si H1 at saka si H2. Right? Now, for this problem to be well posed, kailangan masatisfy niya rin si H3. Unfortunately, the derivative operator or the indefinite or the integral operator is not always continuously dependent on the data. So meron mga special conditions kung kailan nagiging stable o nagiging well posed ang isang differential equation. In particular, the function you're considering should be Lipschitz continuous. Or in the parlance of Math 155, dapat siya ay uniformly continuous. So don't worry kung hindi nyo alam kung bakit kailangan siya uniformly continuous. You don't need to know that. Just believe me for now na para mag-satisfy yung H3, dapat uniformly continuous yung function, yung data doon sa ating dapat uniformly continuous yung right-hand side, right? But when is x squared uniformly continuous? One set or one class of sets kung kailan siya uniformly continuous ay mga compact sets. So yung mga nagwa 155 dyan, alam nila yan. Example ko yan last semester kung kailan uniformly continuous si x squared. Actually, there's a theorem na kapag ang isang function ay continuous, then siya ay uniformly continuous sa kahit anong compact subset ng kanyang domain. But that is saying more than what I should dito sa course natin. So for now, just believe me that this restriction will guarantee H3. Okay? So later na lang natin i-consider case by case kailan nasa-satisfy si H3. Alright? So ito yung isang example ng conversion ng isang ill-posed problem towards a well-posed problem. Okay? Now, one more, let's look at one other case. Consider naman natin yung forward problem characterized by the operator curly M, which takes a 2-vector X. Pag sinabi natin 2-vector, element lang siya ng R2. Or in this case, siya ay 2x1, right? It's a 2x1 matrix or 2x1 vector. So the operator M maps a 2-vector, a 2x1 vector, to another 2x1 vector via the action of the matrix M. So pag binigyan ko kayo ng 2-vector X, ang ginagawa ni operator M, minumultiply niya lang or nile-left multiply niya lang yung given input by the matrix M given by this guy. Right? Now, well posed ba to? Let's see. Let's analyze if this problem is well posed. Essentially, it's matrix multiplication. Right? Pag binigyan ko kayo ng isang 2x1 matrix, so 2x1 vector X, kapag ka handwritten pala, ang vector natin, sulat na lang natin na may bar. Kapag ka typewritten, bold letter yung gamitin natin. Pero pag handwritten, mahirap kasing mag-bold pag handwritten. Lagyan natin ng bar yung mga variables para masabi na siya ay vector. Okay? So kung meron akong vector X, okay, tapos pag minultiply ko siya ng M, unique yung makukuha kong sagot. Right? There's only one way to do matrix multiplication. And we get a unique solution out of it. So that means the operator curly M, right, or the forward problem characterized by curly M satisfies H1 and H2. Unique yung may nag-exist na product yung MX kasi si M ay 2x2, si X ay 2x1. So we get one answer, at least one answer to the matrix product. But we know there's only one way to do matrix multiplication, so we know that there is a unique solution to the matrix multiplication m times x. So that means H1 and H2 are satisfied. Now, to check H3, kailangan tingnan natin ano yung nagiging epekto ng maliit na pagbabago dun sa input, dun sa forward problem, dun sa solution. And when we say a small change, we usually refer to them as perturbation. A maliliit na change sa data, tinatawag nating perturbation. So in this particular problem, we will perturb or we will change the input a little bit or the data a little bit. Forward problem ito. So ang data natin ay yung input. Tapos yung computed output, siya yung magiging solution. Alright? So para matest, gaano ka robust with respect to perturbation? So gaano ka stable with respect to perturbations yung matrix multiplication? Magko-consider ako ng arbitrary perturbation, E. Minsan tinatawag natin si E as the measurement error or the data noise. So magko-consider lang ako ng noise, maliit na noise, i-add ko siya dun sa data. Ang data natin dito ay yung input x. At titingnan ko ano yung epekto nitong perturbation na to dun sa solution. Now, when measuring things, especially kung with respect sila sa dalawang magkaibang scales, we're looking for the relative size or the relative difference. Meaning, ayokong sabihin na ang size lang nito ay 0.1. Kasi baka nga 0.1 yung size niya, pero yung base naman ay 0.0001. So that means it's 100 times the base. So laging tinitingnan ko ay relative size para I'm talking about percentages. Right? So i-assume ko na yung size ng noise o ng perturbation with respect to the data ay epsilon. So kung ganito yung usapan, that means that the noise is about epsilon percent. Alright? So si epsilon parang measure yan ng ilang percent nung data yung nabago. Or by how much percent did we change the data? Para lang level yung playing field. Para sinabi natin na 1% yung change sa input, ilang percent kaya yung change dun sa output. Alright? So kaya laging sanayin nyo na yung sarili nyo whenever describing accuracy or whenever describing changes, laging relative change yung gamitin nyo. The absolute change, i-divide nyo lang by the size of the change. Alright? So kung meron akong noise vector, sabihin ko, maliit lang kunwari yung size niya relative to the data. Oh, by the way, this is the L2 norm. Kapag ka meron kang vector, ang L2 norm ng isang vector in this L2 norm ng E ay equal lamang sa square root ng E1 squared plus E2 squared. The Euclidean distance or the Euclidean length. Yun yung sinasabi natin by L2 norm. Right? So you take the sum of the squares of the components of your vector, tapos kunin mo lang yung square root ng sum na yon. And that would be your epsilon. That would be your L2 norm. Right? So L2 norm nito divided by L2 norm ng input, sabihin natin epsilon units. So that means, itong makukuha kong number na to, ito yung mag-describe ilang percent nung input yung perturbation. Usually 1% up to 5% yung traditional noise na kino-consider natin. Now, titingnan natin ano yung epekto niya kapag pag yung data ay na-influence na ng noise. So instead of just computing mx, titingnan natin ano yung itsura ng m of x plus the noise. Kasi titingnan natin what's the effect of the noise to the output dito sa forward problem. Now, if we carry this out, linear naman yung matrix multiplication. So supposedly ito ay matrix M times vector X plus vector E. Pero alam natin distributive ang matrix multiplication over vector addition. So this is just matrix M times vector X plus ME. Right? And that's what I got here. So pag titingnan ko gaano kalaki yung nabago dun sa solution with respect to dun sa original solution, kukomputin ko ito. Kasi nga, dapat relative change yung titingnan natin. So ano yung effect ng noise of relative size epsilon doon sa solution? So titingnan ko, yung solution after the perturbation of the input minus ano yung original solution without the noise. So we can say this is the noisy solution minus the original solution divided by the size of the original solution. Right? So, computing ko to. So, ito, simplify ko itong nasa loob. Ano yung absolute change doon sa solution? Well, alam ko na yung perturbed solution sorry, yan, hopefully nakabalik na ako. So, ko-computing ko to, itong perturbed solution ay mx plus me. Original solution is just mx. So, mx plus me minus mx is just me. Tapos, original solution ay mx pa rin. Na-edit ko na pala to dun sa version ng module. Dapat ito ay curly m. Pero okay din naman na capital, na matrix m din naman siya. Alright? Now, we will look at this ratio and hope that this is small. All right? Now, property ng norms at saka ng operator norms. Pero just believe me when I do it right now, properties to ng L2 norm ng matrix multiplication. Pwede ko na lang i-multiply yung mga factors. Actually, this is what we call the Cauchy-Schwarz. Dito Cauchy-Schwarz eh. Cauchy-Schwarz kasi ay inequality, Pero yeah, this is a little another version of that. So pwede mo siyang i-factor, but no need to know the technical details right now. So just believe me, etong size nung product ay equal sa product ng sizes. Right? Ganun din yung mangyayari sa ilalim. And now I can cancel the size of M by the size of M below. Matitira na lang yung L2 norm ng E all over L2 norm ng X. But the L2 norm of E over the L2 norm of X was assumed to be equal to epsilon. So that means kapag ka nabago by a certain percent or pag pinerturb natin yung input by a certain percent, the same percentage will be the change in the solution. So you can interpret it this way. Kapag ka tainted by measurement noise yung data by say 1%, 1% lang din yung magiging change doon sa solution. So it seems to be a fair trade-off. Maliit na change in the input, maliit na relative change sa data, maliit lang din yung nakukuha natin na change doon sa solution. So that means we can say that matrix multiplication is or depends continuously on the data. That means H3 is satisfied. So the forward problem of matrix multiplication is well posed. Okay? Now, ano sir yung criterion? Kailan natin masasabi na maliit yung change sa output, maliit yung change sa output? Dito sa example natin medyo madali kasi pareha silang epsilon. So maliit si epsilon, maliit din yung change, yung relative change sa output. Pero hindi kailangan equal sila palagi. The change in the solution might be a multiple of the size of the perturbation. Okay? Pero walang hard and fast rule kung ilang multiple yung pwede. Rule of thumb or a conventional rule of thumb, basta hindi siya lalampas ng 10 times. All right? Halimbawa, 1% na change sa data, all right? Or 1% na noise, dapat hindi lalampas ng 10% yung change doon sa solution. All right? So mga 10 times. Pwedeng mga 10 times, 5 times, and so on. It depends on the application. Kung medical yung application, siguro dapat konti lang yung change in the solution. Kasi you're talking about, say, surgery involving blood vessels. You don't want to be off by 5% in your measurement or even 3% on your measurement. So nakadepende siya from application to application. Pero usually around 10 times, the size of the perturbation is acceptable. So we can still say that it is well posed. All right? So is this analysis of well-posedness making sense? Aside from dun sa mga technical details na hindi ko or na probably hindi nyo pa na-encounter? like yung multiplicative property ng norms. Okay lang na hindi niyo yan alam for now. Ang goal lang natin ngayon, maintindihan kailan siya naging ill post at saka well post. Yung technical details ng mga proofs, that's gonna be for later. Or pag nag-mature na kayo sa curriculum natin, ano? Any questions so far? Diba yan? 5 minutes na lang. Questions? Tahimik nyo, ha? Okay, eto naman. Eto na yung gagawin nyo sa homework. Magpapakita ng ill post. Now, yung matrix multiplication problem ay napakita natin to be well post. Now, the inverse problem is a different story. Okay? So, makikita natin dito na kahit well post yung forward problem, yung inverse problem ay pwedeng maging ill post. Let's see. So consider the same multiplication, matrix multiplication problem, the same operator, curly M with the same matrix capital M. And our problem now is an inverse one, wherein we want to find what is the 2 vector X that should be applied to the operator M to get the vector 2, 2. All right? Inverse problem na to kasi hinanap natin ano dapat yung vector X na magiging input dun sa forward operator such that we get the desired output 2, 2. So it is a specific inverse problem kasi specific yung data na gusto nating i-match. Gusto ko by hook or by crook makakuha ng 2, 2 na solution. So dahil inverse problem siya, we will consider the right-hand side to be the data dun sa problem. Yung desired solution, siya lagi yung data sa isang inverse problem. Alright? So we want to find this kasi si curly M of X ay nag-work lang as matrix multiplication by M. M is the matrix that I gave before, right? Equal siya kay 2, 2. Pero you can note that M is invertible. Balikan natin si matrix M. Ito yung itsura niya. Do you guys remember kailan natin masasabi na invertible ang isang matrix? Anyone in the chat? Or para mas madali, pwede kayo mag-unmute. Para lang may kasama ko rito, hindi naging monologue yung ginagawa ko. Ano yung madaling pang-check kung invertible ang isang matrix? Kasi in general, mahirap computein yung inverse ng isang matrix. Or napapaisip na kayo na mag-drop na sa course kasi ang dami palang kailangang matutunan dito or marami dapat alam. Pero paunti-unti naman yan. Masasanay din tayo. No? Isang madaling pan-check kung invertible ang isang matrix ay kapag non-zero yung determinant. Kunin mo yung determinant ni M, it's a product pababa minus product pataas, it is 0.001. So ibig sabihin non-zero yung determinant ni M, so ibig sabihin meron siyang inverse. Kapag 2 by 2 yung matrix, madali siyang kunan ng inverse. 1 over determinant times, pagpalitin ko itong dalawa na to, tapos kunin ko yung negation nung dalawa na to. So that means, inverse ni M ay 1 over the determinant. Ang determinant ay 0.001, 1 over that is 1,000, times, pinagpalit ko yung nasa diagonal kanina, tapos yung nasa anti-diagonal, nilagyan ko lang ng negative sign. So ito yung inverse ni M. Right? So the traditional inversion scheme will give us a solution X star. Ano si solution X star? Siya lang yung M inverse nung input, right? Remember, our problem is to solve for X such that MX equals 2, 2, right? And nag-i-exist si M inverse. Na-compute ko na si M inverse to be this guy. So apply ko lang si M inverse to both sides. Magiging equal lang to kay associativity uli ng matrix multiplication. Ito equals sa M inverse 2, 2. M inverse of 2, 2 is 2, 0. So that means there exists a solution, and actually the solution is unique. Kasi kapag invertible yung coefficient matrix, unique yung solution ng ating system of linear equations. So H1 and H2 are satisfied. So sabi natin, so dapat so malamang pala ito ay well posed kasi H1 and H2 are met. Tapos yung forward problem ay nasa-satisfy si H3. So malamang masasatisfy din ito si H3. Unfortunately, that's not the case. And let's see why. Mag-consider ako ngayon ng perturbation. Kasi lagi naman ganun, tinetest natin by a noise. Halimbawa, ang noise ay size, ang consider kong specific noise ay 0, 0, and 0.001. Ito yung noise vector ko. Right? And then we compute the size, alright, mamaya na pala yung size. So ito yung noise, specific noise. Ano? So ang gagawin ko lang ngayon, titingnan ko ano yung epekto ng noise na to dun sa solution. Right? So remember, I'll do M of X bar plus E bar. Tapos alam ko ito ay MX bar plus ME bar. Right? Kaya lang yung MX bar, yung solution, alam ko na to ay 2,2. Right? Kasi MX equals 2,2, diba? So ito ay 2,2 plus M times E. Actually, ito dapat ay parang may problema. MX. Ay, baliktad pala. Sorry about that. Pinerturb ko pa lang pala yung data in this particular line. Okay? So nangyari, instead na isolve ko to, this is the original inverse problem. MX equals 2,2. Titingnan ko ngayon, di ba? Tinitingnan natin ay epekto dun sa solution. Ang ginagawa ko ay forward problem. Inverse problem na nga pala tayo. So ito yung data. Ito yung papalitan. Ito yung dadagdagan ko ng noise. Right? Remember, the original inverse problem is this guy. Solve MX equals 2,2. But we are adding noise to the data. Ano ang data natin sa inverse problem? Ang data natin ay yung desired output. This is the data, so siya yung dadagdagan ko ng measurement noise. Okay? Or measurement error. So that means instead of solving MX equals 2,2, I'll be solving MX equals 2,2 plus epsilon or 2,2 plus E. Kasi tingnan ko ano yung solution na makukuha ko mula dito sa perturbed system. We can call it as the noisy data. Kasi yung data mo na ginagamit dito sa inverse problem na to ay tainted by measurement noise or data noise. So instead of our right-hand side equal to 2,2, yung right-hand side niya naging 2 at saka 2.001. Now, it seems not to be a big deal kasi invertible naman yung matrix M that characterizes the operator curly M. So kung isosolve ko si MX equals 2, 2.001, ang solution ko pa rin ay say X prime. X prime ang gagamitin ko para sa noisy solution ay M inverse times the right-hand side, the noisy right-hand side. Ang makukuha ko ngayon ay 1,1. Pero ano yung nakuha natin kanina? Ang nakuha natin ay 2,0. So napakalaki ng pagbabago dun sa nakuha nating solution. A small change, a perturbation of the data in this problem, which is the right-hand side of our inverse problem, ang laki nung nabago niya sa solution because the solution from 2, 0 naging 1, 1. Okay? To analytically justify this, tingnan natin, gaano ba kalaki yung noise relative to the original data. So yung noise vector, yung specific noise vector na kinuha ko ay 0, ito ay 0, saka 0.001. Pag kinuha niyo yung L2 norm, so that would be 0 squared plus 0.001 squared. Kunin ko yung square root, ang sagot 0.001. Tapos yung data natin na D ay 2,2. L2 norm ng 2,2, 2 squared plus 2 squared, that would be square root of 8, so that's going to be 2 square root of 2, which is the size in the denominator. All right, so that means the noise is 3.54 times 10 to the negative 4. So meaning the size of the perturbation introduced is 0.35%. Napakaliit ng change. Pero tingnan natin, yung 0.35% na change dito sa solution, dito sa data, gaano kalaki yung epekto niya dun sa solution? Well, tingnan natin yung relative change in the obtained solution. So tingnan natin yung L2 norm ng original solution, X star, dun sa noisy solution. Remember, the original solution is 2,0. The noisy solution is 1,1. You take their difference, we get the vector 1, negative 1. All right. tas kunin natin yung size nito. L2 norm ng 1, negative 1 ay 1 squared plus negative 1 squared. Kunin mo yung square root. So we get square root of 2. Yung original solution na 2, 0, ang norm niya lamang ay 2. So that means the relative change 71. So that means 70% yung nabago dun sa solution. And it seems to be a big stretch. A 0.35% change in the input corresponded to a 70% change in the output. So that's about 100 times, right? Or about 70 times more than the, di pala 70, about 20 times more than the size of the noise, right? So ang laking pagbabago ng solution, so we say that this is an ill-posed problem. So this is an example of a forward problem that is well posed that has a corresponding ill-posed inverse problem. And unfortunately, ang laking karamihan ng mga inverse problem ay ill-posed. Kaya kailangan nating maging mas careful pag-design ng solution. Makikita nyo rito, yung simpleng inversion ay hindi sufficient para makakuha ng magandang solution sa isang inverse problem. Probably I'll start the lecture on Tuesday by saying more. Bakit napaka-importante ng pag-incorporate noise? Baka sabi mo, sir, naging extra picky ka lang, nagdadagdag ka pa ng noise dun sa solution eh. Titingnan natin bakit siya mahalaga sa mga inverse problems at the start of the lecture on Tuesday. So it's overtime na, so those who have classes can go. And yung mga wala namang gagawin masyado or mga naka-online lang, probably 2 minutes to give you a hint on the homework. Those who will miss this can go back to the solution, but before you leave, if you answered, may mga nag-answer ba ngayon ng verbal? Kung may nag-verbal recitation ngayon, pa-comment naman dun sa chat. Pero dun sa mga walang masyadong hahabulin, siguro clue dun sa homework, Hold on. Okay. So clue dun sa homework. Halos katulad din nung nandun sa example. Meron tayong inverse problem characterized by matrix A times vector X equals B, given si matrix A, given si vector B. All right? Tapos, hold on. Okay. Hindi ko pa kasi na-discuss pala yung second example. Kasi nga pala hindi invertible tong matrix na to. So, lucky for you guys, kailangan kong i-postpone yung homework. Alright? So, hindi ko muna i-do yung homework kasi kailangan ko pang i-discuss yung pseudo-inverse. Those who have taken 175, kilala nyo na yung Moore-Penrose pseudo-inverse. Pero for the benefit of those who haven't taken 175 yet, alright, i-discuss ko next time kasi mamroblema sila. Paano na isosolve yung AX equals B si A ay hindi invertible? Hindi nga siya square siya ay 3 by 2. So walang inverse ang isang 3 by 2 matrix. Paano natin siya isosolve? Probably I'll start with this on Tuesday. So lucky for you guys, you will have a nice weekend insofar as Math 191 is concerned because homework number 2 is postponed. Right? Nakalimutan ko na 3 by 2 nga pala yung binigay ko sa homework. So I'll stop here. Sorry, overtime na naman ako, especially for those na kailangan pa tumakbo sa kanilang face-to-face classes. But any urgent questions? Parang unti lang nung math na diniscuss ko ngayon, pero parang ang haba nung oras na ginamit ko. Masyado yata akong madaldal, maraming side comments. Pero okay lang yan, para napo-postpone lagi yung mga homeworks nyo, So if there are no further questions, then again, postpone yung homework. Lucky for you guys. So I hope you have a good weekend. Let's see each other again on Tuesday. All right? Bye, guys.